Before discussing how to make statistical inferences about the usefulness of multiple linear regression, we will consider a popular descriptive measure of the utility of the sample regression equation. So how do we measure the relationship between the DV and several predictors? As we talked about in bivariate regression, the residuals are the error in regression. And this is also the case in multiple regression. The symbol for bivariate multiple correlation coefficient, the Pearson correlation coefficient, is little r. The symbol for multiple correlation coefficient is big R. While little r has a range from -1 to +1, which I talked about in the bivariate regression and correlation lecture, big R only ranges from 0 to 1, which is from no relationship to perfect relationship. Now, the larger the big R, the stronger the relationship between the combined independent variables and the dependent variable. And the more accurate we can predict the dependent variable scores based on the independent variables, and the smaller the combined residuals. Now, R squared tells us the proportion of variance in the dependent variable that's explained by the combined independent variables. The combined residuals represent the proportion of variance that's unexplained by the combined independent variables and must therefore be accounted for by other things that have not been included in our regression model. Remember too that a great many variables will be associated with any one dependent variable, and we'll never be able to accurately account for 100% of the variance. Our aim is to account for a substantial proportion by identifying the main variables involved. In theory, you're predicting an outcome from a number of variables rather than just one, but you want to add the additional variables only under certain conditions. So let's stay on this example. Number of dates is equal to A plus B1 attractiveness plus B2 personality. This is a multivariate relationship between the criterion, which is number of dates, and the two predictors, attractiveness and personality. Now let's say we wanted to add amount of time socializing into this mix. So all of a sudden we've got this equation behind us, this linear multiple regression equation. B1 is the coefficient for attractiveness, B2 is the coefficient for personality, and B3 is the coefficient for time spent socializing. Now when I add a new variable of time spent socializing, it should make a unique contribution to the understanding of the dependent variable. Otherwise, why use it? So what do we mean by unique? Well, the additional variable needs to explain differences in the predicted variable that the other predictors don't. That is, the three variables in combination would have to predict y, or the number of dates, better than one or two of the variables would do alone. Multiple regression remains pretty straightforward when the predictors, the independent variables, are uncorrelated. In this case, the individual correlation with the dependent variable is additive. The problem is that this situation pretty much never occurs in the real world. In the uncorrelated situation, big R squared is the sum of all the little r squareds for each independent variable with the dependent variable. This can be illustrated by a Venn diagram. So let's say we're estimating the number of dates that a person has had, and we have three independent variables of attractiveness, personality, and time spent socializing. The multiple regression looks a bit like this. Now here's a Venn diagram that shows a situation where these three variables are uncorrelated with each other. So imagine that the blue circle represents all the variance in the dependent variable, in this case the number of dates in the last 3 years. This is the outcome variable, or the dependent variable, and it's designated as y. The red circle represents all the variance in the first predictor, x1, which is a score of the person's attractiveness. So as you can imagine, different people have different scores on attractiveness. The greater the difference in the scores of people's attractiveness, the larger the variance of this predictor. The brown circle is all the variance in the second predictor, x2, which is a score of the person's personality. Not everybody has the same personality. The larger the differences between people's personality, the larger the total variance on this measure. And the green circle is all the variance in the third predictor, x3, which is the amount of time people spend, or the person has spent, socialising. Some people don't get out much and would score little on this. Other people get out quite often. The greater the difference in the scores on this predictor for the sample, the larger the variance. Now the red coloured portion then represents the shared variance of x1 and y. In other words, a variance of x1 that explains the variability of y. The brown coloured portion then represents the shared variance of x2 and y. In other words, a variance of x2 that explains variability of y. The green coloured portion then represents the shared variance of x3 and y. In other words, a variance of x3 that explains the variability of y. Now, when independent variables are uncorrelated, their individual correlations with the dependent variable are additive. And to find the big R squared, one simply adds the little r squared values for each independent variable. Overlapping shared areas represent the variance that is shared between variables. In other words, the little r squared between variables. So big R squared equals the sum of the little r squared for each independent variable. So the big R squared in this example is 0.72. This means that the proportion of variance in the number of dates that is explained by the linear combination of all three independent variables is 0.72, or 72%. Having uncorrelated independent variables in the social and behavioural sciences is really quite unrealistic. It's far more likely to have independent variables correlated with each other or amongst themselves, so the IVs are correlated amongst themselves. And this makes multiple regression much more complicated because we can no longer add the little r squareds to arrive at the multiple r squared. When independent variables are correlated, the researcher is interested in their unique relationship with the dependent variable. That is, that part of the relationship with the dependent variable that cannot be attributed to or is not associated with their relationship with other independent variables. This shows another situation with three predictors. Fear of crime is equal to A plus B1, past victimisation, plus B2, past incivilities, plus B3, age. As you can see, the predictors are overlapping amongst themselves, which indicates that they themselves are intercorrelated. The large R squared is represented by all the shaded areas. That is, the yellow, the green, the red, and the brown. This is the proportion of variance in y that is explained by the linear combination of the independent variables. Or to use this example, it's the proportion of variance in the fear of crime that's explained by the linear combination of past victimisation, neighbourhoods, incivilities, and age. The yellow shaded areas, they represent the overlapping portions, and the yellow portion in the very centre represents variance that's shared by all three predictors. So now if we add the little r squared, what we will do is we'll overestimate the big R squared to the tune of what is contained in the yellow areas. What becomes of interest now is the unique relationship of each independent variable with the dependent variable. The proportion of variance that it and it alone shares with the dependent variable. So here for x1, it's represented by the red shaded area. This is a portion of the big R squared that's uniquely attributed to past victimisation. It's known as a squared semi-partial correlation and reflects a semi-partial correlation of past victimisation with fear of crime. The proportion of variance that it and it alone shares with the DV. For x2, this is the brown shaded area. This is the portion of R squared that's uniquely attributed to past incivilities in the neighbourhood. And it's known as, again, the squared semi-partial correlation and reflects that semi-partial correlation of past incivilities with fear of crime. And the proportion of variance that it and it alone shares with the dependent variable. For x3, this is the green shaded area. This is the portion of R squared that's uniquely attributable to age. And again, it's known as a semi-partial correlation, or the squared semi-partial correlation. All the yellow shaded areas are shared among the IVs, or the independent variables, and so cannot be uniquely attributed to any one of them. Now, if you look at this figure, and the three predictors all seem to have a reasonable overlap with y, but their unique overlap is rather smaller, especially for x2, which is a variable for past incivilities in the neighbourhood. Now, I would not be surprised to find significant correlations with y for all three variables, but non-significant semi-partial correlations for x2. This highlights another problem of correlated predictors. In standard multiple regression, all the predictors are entered simultaneously. In standard multiple regression, we simply assess the multiple R squared. This is a proportion of y that's explained by the linear combination of the independent variables. This is all the coloured bits, red, brown, green and yellow. Then we assess the unique contribution of each predictor. This is the red, brown and green proportions in this Venn diagram. So what this can mean though is that a variable such as x2, in this case past neighbourhood incivilities, that might have a significant simple correlation with y, yet fails to have a significant unique relationship with y. This is the brown bit that's left. So in other words, it can get eliminated from consideration because it adds nothing to the significant prediction of y over and above what is explained by x1 and x3. But what if x2, or past incivilities in the neighbourhood, was a causal predictor of x1, which is past victimisation? In other words, what if past incivilities causes variance in past victimisation? By dismissing past incivilities, we might be distorting our understanding of what's going on among these variables. While this lecture is about standard multiple regression, this problem highlights a rationale for hierarchical or sequential multiple regression, in which variables are entered according to priority order, for example, according to causal, theoretical or practical ordering. I will not be going into this in any detail in this course or in this lecture. I will now highlight the assumptions that need to be taken into account in multiple regression, in addition to the interpretation of the SPSS output in multiple regression.